My name is John Handler. I'm a solutions architect with AWS. I work with our search services, specifically Elasticsearch and Cloud Search. And today we are going to talk about Elasticsearch service. Oh, I got to do my button. OK. That's me, John Handler. So out of curiosity, who is currently using Elasticsearch? Very large number of people. That's great. So a lot of you are going to know some of this background material pretty intimately. As we look at it, we are generating tons and tons of data, and we're generating more data all the time. Back when I was a baby hacker, we had like 10 megabyte disks, and boy, we were happy. And everybody remembers that 640 KB thing. So, and in fact, we see a lot of different places where this is coming. Specifically, we see a lot of movement down in the organization. So a lot of developers are generating data from their applications, they're generating log data from their infrastructure, and they're directly interacting with that data. They want to monitor, they want to figure out what's going on with it. We also have tons of IoT devices out there, everything from temperature sensors to smart buildings to taxis, all of that stuff. And finally, we have cloud-based architectures where if you're putting an architecture in the cloud, building an application in the cloud, you'll be generating log data from all of that. You'll be generating CloudTrail logs, you'll be generating EC2 logs, your application logs. All of that is going to be coming. So, and really, the emphasis there is on the ability to dig in and really get a real-time feel for what's going on with your application or your hardware based on what's the log data that you have. And Elasticsearch came out in 2009, and it's very easy to deploy. It's very easy to get your data into it. It's an open source piece of software, and it's compelling. There's a really fast time to value. It's very easy to deploy it, send a bunch of data in, and you're visualizing it very quickly. And all of that has pushed Elasticsearch to the top of open source projects. This is from TechCrunch, Elasticsearch number 7 on the list of open source products in terms of popularity. Now, the wrinkle with it is, with Elasticsearch, it is very easy to get started, but as your data size grows and as your deployment grows, it becomes more difficult to manage. So 2 years ago, we came out with Amazon Elasticsearch service that makes it easy to deploy and scale Elasticsearch in the AWS cloud. We have a number of things that we provide. First of all, we provide an open source compatible version of Elasticsearch. So if you're already using Elasticsearch and you're using it self-managed, you can bring that into the service easily. We do the management and overhead and undifferentiated heavy lifting work to manage that cluster for you, and you can use the same open source tools and APIs that you're already using. Second of all, we make it easy to use. So with Amazon Elasticsearch service, you use the console, SDK, CLI, what have you, to deploy an Elasticsearch cluster. We do the work of bringing all that in, making a cluster out of it, configuring it, and bringing it to you over an endpoint that you can use the Elasticsearch REST API. We make it easy to scale. With Elasticsearch service, you can change the underlying pieces of your infrastructure. So if you'd like to go from an M3 2x large to an R3 8x large, just a few commands, and we will redeploy a new cluster for you. And we'll do all of that work seamlessly, so you continue to use your cluster. It's all behind load balancing. We have a number of different security options. So you can use IAM and VPC together or separately to secure access to your cluster and make sure that only the right people get to view the information that you want them to view. We have a high availability feature. This is called multi-AZ. We simply split your cluster into 2 zones. You have 100% data redundancy in each of those zones, makes your cluster more resilient. And finally, we have a lot of integrations with other AWS services. On the ingest side, you can send data from CloudWatch logs directly to Elasticsearch service. You can use Kinesis Firehose to send data to Elasticsearch service. You can send it from IoT. And on the cluster creation side, CloudFormation does support Elasticsearch service as well. We see a number of different uses of Elasticsearch service. So in particular, the main use case that we have is for application and infrastructure monitoring. So most of our customers are sending logs into Elasticsearch. Those logs are Apache web logs, they're syslogs, what have you. And they're using Cabana to visualize what's going on with their application or with their hardware to make sure things are up and running. We also see a number of SIEM use cases, things like denial of service, fraud detection. People are using their logs, sending them in, and then being able to pull out that kind of information. In the IoT space, of course, IoT data goes in there. You have nice graphs and charts. You can see what's going on. And then finally, at a business level, we do see a lot of data flowing in from logs that allows business users to figure out how the software is being used, what people are buying, what people are doing with the software, and how to improve it. I'll just mention a couple of case studies for you. So the first one of these is Expedia. Expedia had tons and tons of logs, and again, driven very bottom up by individual developer groups that were deploying Elasticsearch with their application so that they could do development work and monitoring of that application. You know, as a corporate model, we do see a lot that when we have these very scattered use cases, there's a drive to bring them into a more centralized architecture so that people are more successful with being able to monitor their software. So they have come onto the service. They are streaming a number of different log types, and they have a centralized logging service with Cabana that allows their developers to deploy that and use it. Another interesting use case, this is more of a business data kind of use case. So Financial Times is an online media, amongst other media companies. And they are sending their web traffic logs to Elasticsearch. They have an internal tool which they call Lantern, and Lantern allows their journalists, number one, to go look and see what is the world doing with their articles. What's the interaction like? How long are people dwelling? It's a nice thing for the journalists. They get the immediate feedback of knowing that people like their content. On top of that, the editorial board is able to use this information, this analysis, to figure out how to target content and what to bring out. We have a number of customers who are using Elasticsearch service. These range in scale from very small to very large. The thing that is interesting about this slide is we have so many different segments that are all using Elasticsearch service. Primarily, they're using it, again, for this kind of real-time monitoring where they're able to see what's going on with their hardware and software. So there's not a particular segment-directed usage of Elasticsearch. It's across the board log monitoring. We have a number of different topics that we'll cover today. Some foundational stuff. We'll talk about ingest, security, durability, monitoring, and also a little bit of analysis. So, I love this slide. So, who has something that generates logs? Okay, right, everybody, yeah. And, you know, when the pager goes off and it's 3 in the morning and the servers are melting and your boss says, you need to get in there and figure it out, right? And then you have this. This is an Apache weblog. In fact, it's from NASA, but it's an open source weblog. Let's say I have, you know, a terabyte of that, right? What's the first thing I want to do? I want to reach for my search tool so I can find the thing that's broken, right? This is human readable, but it's not useful in this format, right? And beyond that, what I'd like to do is I'd like to have a nice interface that lets me visualize in some way that's meaningful what is going on under the covers. So I have a little demo. This is actually from a lab that we're going to be running Thursday. What we've done is we created a little sample application that allows you to search through a movie database of 5,000 movies. The search is actually powered by Elasticsearch as well, so Elasticsearch is good for text search as well. On the individual application nodes, we have a technology called FileBeat, which is sending the Apache weblog lines through Redis, which is buffering, into Elasticsearch. We're then able to use Cabana to visualize what's going on with the cluster, with the application. So this. And all of this is happening in a VPC. So I actually have an SSH tunnel I'm running from my laptop, which is talking to my VPC, which is talking to the Elasticsearch cluster in my VPC. That lets me use Chrome here to connect to the cluster. All right, let me just make it a little bit bigger. Okay, so this is the application, right? So it's a very simple application. I can simply type something like Gwyneth Paltrow, say, and I'll see some movies by Gwyneth Paltrow. I don't see Iron Man here, which is my favorite movie, so let's go ahead and search for Iron Man, and we can get titles like that. So this is totally obvious. This is the stand-in, like I'm just running some kind of search application. So what's also happening, again, we have data that's coming from my weblog lines, and this coming into Cabana. Now this is the Cabana UI, and you can see here I have a graph at the top, which is showing all of the traffic to my website. I have also here some example log lines that are coming in, right? So I can look at one of these. Can you guys see that? Yeah, pretty much. Let me see if I can make it bigger. You'll see here, these are all the pieces of the message itself, right? So here is the Apache web message. That's what's coming out of my log line. Data that goes into Elasticsearch gets structured into JSON and split into individual fields. Those fields are searchable. They're also visualizable, right? So some of the things that I have in here that are broken out, here's the straight up request, here's the response code, et cetera, et cetera. I can also build visualizations. So I have a number of different visualizations that I can build, including charts and graphs and line graphs and pie graphs, all of these things. So I can do something pretty simple. I can simply go in, and you have to think of this like an OLAP queue. Okay, so I have fields in there, and I'm able to create buckets based on ranges of values in those fields, and I'm able to subdivide those buckets to create visualizations. So for this particular visualization, let's say I want to know how much data am I pushing out of my web server, right? Over time, so the first thing I need is on the x-axis, I need to have a graph, which is the time. If I set that one up, you can see here, this is actually just a graph of all my requests. You can see the couple there where I send for movies, right? But what I actually want is a sum of my traffic out. These are the kinds of aggregations, these are the kind of functions I can compute for the y-axis. I have things like the sum and the medium and the min and the max and the average. All of those things I can compute and put on the y-axis, but I'm going to pick sum, and I'm going to go ahead and pick the byte field. All right. So this is a sum of bytes. I can also save that, and I can build a dashboard out of it. The dashboard is really where things become interesting and useful. So this dashboard has a number of things on it, including a total number of requests. Here's my traffic graph. Here's an average of the bytes out from my server, IPs and requests. This is a breakdown of source IP and what is the actual request that it made. I have agents. This is the agent field in the weblog line. I even can have a keyword cloud. We can see my keywords there. So I'm going to take this one quick step further. I have JMeter set up. JMeter is hitting the application with URLs and is doing searches in the application for 1 to 5 words. So if I do that, so now I have 25 threads running, and I'm also here going to enable my auto refresh. So with Cabana, I can set an auto refresh so that my graph updates. And you can see, my traffic is starting to come in. So this is the kind of the power of Cabana, is to be able quickly, this dashboard took me maybe 20 minutes to set up. And yet I have tons of useful information that's updating in real time as traffic is coming to my website. So let's talk a little bit about how we set that up and what are the pieces, how do I put them together. So in particular, when I use Amazon Elasticsearch service, I deploy what we call a domain. A domain wraps a number of different pieces of hardware, the software, and all of the portions of Elasticsearch that you use. In particular, we have a number of different instances. So we have data instances and master instances. We have load balancing in front of the cluster. That's sending the traffic across all that. We have IAM that you use for security to control access to the different pieces of the cluster. And we send logs to CloudTrail and CloudWatch logs. When you use Elasticsearch, when you use any search engine, really, a document is a core entity of the search engine. A search document is what you send into a search engine. It's what you get back from a search engine for a query. Okay? So the document is the core entity. And as I said, a document is structured JSON. Okay? So if we take that Apache weblog line at the top, then we break it down into JSON that looks like what's on the left, and that gives us the document that we're sending to Elasticsearch. The documents contain fields, and a field is a name-value pair. So in this case, we have a field for the verb, which is get. We have the bytes, we have the request, we have the response, etc. We break it all down like that. Within Elasticsearch, fields can nest, and there are tons of different value types. And you can have single or multiple value fields. For weblog lines, it's always flat like that. So when you send documents to Elasticsearch, you send them as JSON just like that. And Elasticsearch stores those documents in an index. Index is a high-level structure that contains documents, right? We're not talking here about indexing the values yet. So in this case, the documents go into an index. That index is logically composed of a number of shards. Each shard is a subset of all of the documents in the index. So in this case, we have 5 primary shards, and each of those shards contains 1/5 of the documents in the index, not overlapping. Okay? We can also set dynamically a set of replicas. So the first set of replicas we want for redundancy, so that we have data in 2 places within the cluster. And we can add additional ones for additional capacity. The shards themselves, Elasticsearch distributes onto nodes in a cluster, right? So we have some instances, in this case we have 3 instances. We have our primaries and our replicas are distributed onto the instances in the cluster, with the important feature that primary and replica always go onto different instances. Okay, so if I lose a single node and I have a replica, I have a copy somewhere. And then Elasticsearch can recreate that primary or replica. And then finally, each shard itself is actually an instance of a process which is running something called Apache Lucene. Apache Lucene is a Java library that reads and writes search indexes. So when we look at it, the shard itself is the main components, the main piece of scale, right? Elasticsearch is distributing all of this stuff to parallelize across a number of instances. The shards themselves are what do the actual work. Okay, so that's our foundation. So let's talk about how to get data into Elasticsearch. When we think about ingestion, there are a number of different parts of ingestion, a number of different pieces that you can think about. First of all, you have a data source somewhere. That's going to be your web server. That's going to be your S3 bucket. It's going to be your Dynamo table. It's going to be what have you. Somehow you have to take the data from that source and collect it. There are a number of different technologies or pieces that can do this as well. For servers, we have Beats, which is an open source product that pulls or tails your log lines. We also have Logstash. We have the Kinesis agent, the CloudWatch agent. All of these can sit on your server, tail your logs in a lightweight fashion, and push them off to somewhere. After the logs are collected, then they do need to be transformed. As we said, they started out as strings, they need to be JSON. So something has to transform that. Then depending on scale, but usually you also want to have a buffer in place that's going to hold those log lines, create batches out of them, and deliver those batches to Elasticsearch. And finally, there's the delivery piece. So we'll talk about a number of different architectures, but in the back of your head, think about the jobs that they're doing, and you can slot many different things into each of those pieces to accomplish the task, right? So some of the more AWS centric architectures involve, number one, the data producers, and then Kinesis Firehose and CloudWatch logs performing the buffering and transform. IoT can also do that buffering and transform. Logstash is, again, an open source option for sending that data through. It also does buffering and transform. That data is arriving at the Elasticsearch service cluster. And then the access to that data from the front end is via Cabana. That's one set of options. There are another set of options that serve different use cases. So like the first one, where we have files, perhaps they're enterprise files, perhaps they're even files of logs that are landing in S3 as your data lake. You then have Lambda that can trigger on those object creation events to read those files, parse them, transform them, and send them off somewhere. Usually this one, you'll need a buffering solution in here. From DynamoDB, we have Dynamo Streams. Again, you can trigger Lambda off your Dynamo Stream to push data to Elasticsearch as it changes in your table. And then finally, we have Kinesis Streams, where you can have the Kinesis client on your data producer pushing to a Kinesis stream. Lambda can trigger off of that, do a transform, send it somewhere else to do a transform, buffer, etc. I like to mention Kinesis Firehose because Kinesis Firehose has some really great characteristics for Elasticsearch traffic. Number one, it is serverless, it scales almost infinitely, and it affords you the opportunity to do the transform in line. So with Kinesis Firehose, you can trigger a Lambda for all of the events as they're coming through that Firehose. You can transform those records, return them to Firehose. Firehose will deliver them. So that nicely takes care of transformation and buffering. Firehose also deals with errors. So if documents are not delivered to Elasticsearch, Firehose will put them in an S3 bucket for you. You can come back, so essentially you have a dead letter queue built in. You can adjust Firehose buffer sizing, so Firehose does the buffering and you can adjust. And then finally, you can also deliver all of the source records to S3. So if you need to have a backup of that data as it's coming through, you can easily have Firehose send it off to S3. So Firehose is a great option just in general for getting data into Elasticsearch service. All right, let's talk about sizing. So I talk to many, many customers, and I would say everybody struggles with scaling Elasticsearch. It's kind of one of the fundamental challenges of it. And when you come to the service, you're confronted with, okay, I need to figure out my deployment, and how many instances do I need? How many shards do I need? How do I get this thing deployed right? And my one piece of advice, and it's simplistic, but it's kind of true, is to use storage as your yardstick when you're trying to figure out how to initially size your cluster. After that, you're going to have to monitor and check and make sure and adjust, but to get started, size is the thing to work on. So if I think about how many instances do I need, and I think about that in the context of storage, I have to know, okay, well, given some amount of data, how much storage do I need, right? And it turns out that when you send data into Elasticsearch, it inflates a little bit in the index, but not a lot. It's about 1.1 to 1. So for all intents and purposes, and because you're taking the first simple pass, you can just say 1 to 1. If you're going to deploy a replica, remember, Lucene is storage, so you need to double the storage you need. And then you can size your instance count based on how much storage you're putting per instance, and just divide. So if I have a 2 terabyte corpus, and I'm deploying 1.5 terabytes of storage per node, I need 4 nodes, because I have 2 terabytes of corpus, let's call that 2 terabytes of index. I have a replica, so I have 4 terabytes of storage that I need. And then I have 1.5 terabytes of storage per instance. So given overhead and squinting at it, 4 times 1.5 terabytes, 6 terabytes, sounds like a good size. Oop. Oh, come on. Thank you. Similarly for shards. So the best practice for shards is that each shard should be no larger than 50 gigabytes, right? So you can divide your total index size by about 40 gigabytes to have a first cut at how many shards you need. 40 gigabytes because you want to leave a little overhead, right? And if I have, again, a 2 terabyte corpus, I'll need 50 shards. Because I have 2,000 gigabytes, I want 40 gigabytes per shard, I need 50 shards. A couple other points. You kind of want to keep your shards in line with your number of CPUs. So we're going out of the storage realm here, but this is to a first approximation. You may have to adjust if you have too many shards. You may have to add instances. And always use a replica, at least one, for any production workload. Because that replica, again, gives you data redundancy. You don't want to lose your data. We support a number of different instances in the service, and it can be a little bit confusing. Which instance do I want to pick, given my workload? Number one, we have the T2s. The T2s are OK for dev and test. And my slide is lying. They're not OK for dedicated masters. The T2s are fine instances, but I wouldn't put them in a production setting, not with Elasticsearch. With the M class of instances, we have equal read and write capacities. Those are a good general purpose place to start. That's our default instance type is M4 large. That's an excellent place to start. With the R class instances, we have additional RAM. And you can get out to really large RAM sizes. Now, in fact, Elasticsearch is a Java application. And a Java application has a heap. And probably you know you don't ever want to run the heap larger than 32 gigabytes. So you may say to yourself, well, OK, I have a 244 gigabyte R38X large. What's the point of running Elasticsearch on that instance? Well, if we think back, Lucene is a storage-based solution. So it's M-mapping all of the index data into memory. If I have 210 additional gigabytes, the operating system will cache all of that data. So the R instances really can give me a big speed boost because all of my indexes get cached into RAM, and essentially I'm running RAM resident. So the R class are good for heavier workloads or workloads that require more RAM. The C class, we use that for a high concurrency because the additional CPUs gives you the ability to handle more requests concurrently. And the I class has the largest ephemeral storage for any instance. So the I class is good if you have a very large use case and you need that additional storage. Just a quick sidebar on storage. We support both EBS and instance storage, ephemeral storage. And the question is, what's the difference there? Is EBS the right storage choice? We find in most situations that EBS is perfectly acceptable, especially for these real-time logging kind of use cases. EBS works great for those use cases. You do find it's 10–15% slower than ephemeral storage, but again, for this use case, it is perfectly acceptable and gets you bigger storage on smaller instances. So as we said, we started with sizing, but then we have to make some adjustments based on what is the workload. This is a thesis's worth of information, and there's no way to cover it all, but I'm going to try and point out a couple of things that will help out as you test and monitor and try and figure out. So we have two kind of classes of use cases. We have a write-heavy class of use case. This is the log analytics use case. And we have a read-heavy use case, which is just the full-text search like my movies application. And you want to scale those a little bit differently. So number one, in both cases, you have to pay attention to concurrency. As you're sending traffic through, you're engaging those shards. That means they have to run on a CPU somewhere. If I send 1,000 requests in a second, and I have 2 CPUs, it's not going to be successful. I just don't have the capacity there. So I have to make sure that I have enough CPUs to handle the concurrent readers and writers that I want. And then there's a setting on the right side called index.refresh interval. This is a really great setting. It's a good knob that gives you up to 75% or so more capacity. What this controls is how often does Elasticsearch or Lucene actually flush data to disk. The data is not searchable until it's flushed. It accumulates in RAM, and then it gets flushed to disk. The default here is one every second. Now, that's fine. If I increase that, though, I decrease the writes to disk, and I decrease the amount of work that Elasticsearch has to do with those pieces of index, right? So in this case, if I go to 30 seconds, I get 50 to 75% more capacity in the same instances. The downside is that puts a delay of 30 seconds before I can actually read that data. For write use cases, you scale horizontally by adding primary shards and instances to hold those shards. Okay, so the more primary shards you have, the more you're distributing your writes across those instances. For read use cases, you want to increase your replicas, not your primaries. You increase your replicas and add instances. Your replicas give you additional read capacity. Monitor, monitor, monitor. Always monitor. That's the only way to figure out how to right-size your cluster. There are a number of different things that we provide through CloudWatch. Also, Elasticsearch APIs for monitoring are open so that you can read what's going on in the cluster down at the file system, at the operating system level, CPUs, all that stuff is open. You have to look at that to figure out what's going on. When you look at how your shards are distributed across your cluster, there is a sort of sweet spot that looks like the number of shards per node is roughly equivalent to the number of CPUs. It's not precise, but that seems to be where the sweet spot is. So if you think I have 50 shards and I'm going to run on 4 CPUs, probably 10 instances is what you want there. Sorry, yes. And then beware, because Elasticsearch actually distributes the shards based on shard count, not shard sizing. So you can get into situations where you have lots of little shards and then a few big shards, and then that causes log jams in your cluster. Okay, let's talk a little bit about security. So we have 2 different options within Elasticsearch service for where the endpoint sits. So your endpoint can be a public access endpoint. That means it's a public DNS entry to a public endpoint where your traffic goes. If you choose that option, then you're going to use IAM policies to secure your cluster. The second option is it can be in your VPC. So it will be a private endpoint within your VPC, again, resolved through DNS, but to a local address within your VPC. In that case, you can use security groups and inbound and outbound rules to control access to the cluster. So this is, if you're in the public access scenario, you use IAM to control access to that cluster. So here's a skeleton IAM policy with a number of different pieces to it. The first is the effect, so you can allow things and you can deny things. There is a principal, which can be an AWS user, account ID, role. So this identifies a principal within AWS. If you specify a principal, you have to use SIG-v4 signing to sign the request. That's how we do the authentication and access control. There is an action. The actions include the HTTP verbs as well as the service commands. So you can specify, and the HTTP verbs matter because Elasticsearch implements a REST protocol correctly. So get is an actual read from the cluster, delete you use to delete indexes, and like that. So this gives you some granularity in terms of the Elasticsearch API, which commands you're allowing or denying for a particular user. As well, the service actions, you want to have administrators, you want to have various actors, and who can do administrative or other service level things. The resource that you specify is your ARN for your domain. You can have full domain access control, or you can have access control down to an index level. So user Sally can read from index, my big logs index, or what have you. And then finally, you can specify an IP address or sitter block for the policy. This will restrict access to a particular set of IP addresses. So we now support Elasticsearch in VPC, and this is supported through ENIs within your, Elastic Network Interfaces within your VPC. The traffic itself is private, so it goes between your VPC and the Elasticsearch cluster and does not go to the public internet at all. You can use both IAM policies and security groups to secure this traffic between your application and the cluster itself. So just a quick architecture for how you might do that. In this case, we have some producer nodes. Those are sending data via Logstash to a load balancer. That is an auto-scale group of Logstash instances that are taking that traffic and indexing it to Elasticsearch via those ENIs. And then again, we stand up a Bastion host that lets me SSH in or tunnel in or in some other way proxies the cluster so that I can access it through Cabana. So we have our data in there, we've got it in our VPC, we have our security set up. So how can we make this solution a little bit more durable? So number one, we have a feature we call, Elasticsearch has a feature, it's called dedicated masters. So let me explain a little bit about this. Every cluster, every Elasticsearch cluster has a master node. That master node keeps track of the cluster state. And the cluster state includes things like what are the different instances, where are the shards, what are the schemas for each of the indexes, and that master node is responsible for distributing that information across the cluster. You could kind of think like zookeeper node. So if I have a cluster with no dedicated masters, one of those cluster instances will be elected as the master. And its job will be to do the master function and to do the data function, like write data and respond to queries. Now, the problem is if I have a lot of traffic, my master node can become overloaded. And when that happens, my cluster goes away. And that's a bad thing, right? So putting the master function and the data function on the same instance is not the greatest idea, certainly not for production. So what you actually want to do is you want to say, okay, let's get some master nodes, and that's all they're going to do. They're just going to do the master function. And we can do that with the service. Then the master itself is elected from the dedicated master instances, and those nodes are just doing the master thing. They're just keeping track of state. So number one, they can be a lot smaller than the data nodes. But they're very important for stability. Now, you want to have 3 dedicated master nodes. Why do you want to have 3? So the master itself, again, is elected based on the majority of voting nodes. If you have an even number and you have a network split and you have, say, 2 in this one and 2 in that one, each of them can decide, oh, I'm a cluster. And then you have your data going in 2 different places and everything falls apart. It's bad. So even is bad. So you want to have an odd number of masters, and actually 1 is not really sufficient, right? So the first odd number bigger than 1 is 3. So 3 is the right number of dedicated masters. Sometimes for really big clusters, you might want to have 5, but generally speaking, 3 is the right number. Your instance size, as I said, is going to be smaller, probably, than your data nodes, right? So here's our recommendations for master nodes based on how many data nodes are in the cluster. If you have fewer than 10, M3 medium. If you have 50 to 100, C4 2x large. And you can see it sort of scales up. Always use an odd number of masters more than 3, and they can be smaller than data nodes. Zone awareness is another durability feature, and this will essentially take your cluster and split it into 2 different availability zones, right? So in this case, we evenly divide the instances, and then we make sure that primary and replica shards end up in different availability zones. Should a full zone go out, you again retain 100% of the data in the second one, and Elasticsearch can then recover from that. This we also recommend for all production workloads. right, let's talk about monitoring. Monitoring is really important. Number one, we publish a number of CloudWatch alarms. And these alarms are there for you to make sure that your cluster is running okay. So just to talk a little bit about some of them, cluster status red means that your cluster has gotten into a red state. A red state occurs when some data has been lost. So that's an important one to understand and pick a threshold of 1. If it ever happens, you want to know that some data is gone. Also, when you fill your cluster too much, then we start sending back a write block error. So if your cluster has become overly full, or we can't deploy a shard somewhere, you want to know that. So the threshold is 1, just 1 period. You want to go and look at that. We also publish the CPU utilization metric. I find it's okay to run Elasticsearch up to about 80%. Above 80%, you start to break down a little bit. You don't have enough extra CPU for all of the administrative tasks that have to happen. So you want to keep the average CPU below 80%. If it goes above for 3 periods, that's a time you want to alarm and say, oh, maybe I need to think about my scale here. In the JVM memory pressure, the JVM memory pressure measures essentially the effectiveness of garbage collection. So normally you'll see that number bounce between 50 and 75%. If it breaches 75%, you're on the way to trouble. So 80% is a sensible line to set there and alarm on that and start thinking about remedies in terms of adding more instances or larger instances. Free storage space, pretty obvious. If you run out of storage space, you're in trouble. But the recommendation here is that you take 25% of the available space, and if you drop below that, it's time to start doing something. And then finally, we take automated snapshots. If one of those fails, you probably want to know that. In addition, we've released a feature where you can publish Elasticsearch's slow logs to CloudWatch logs. So what are the slow logs? The slow logs are logs that contain requests to the Elasticsearch cluster that take longer than a particular threshold. As you can see here, we have a number of different thresholds that we can set. We have a warn, an info, a debug, and a trace. And we can set them at different millisecond values. So I want to know if, I want to log all of the queries that ran for longer than a second. I can enable this. They go to CloudWatch. I can then look at them in CloudWatch, send them back to Elasticsearch, what have you. And finally, let's talk a little bit about how Elasticsearch analyzes your data. So if you think back to sort of the construction of the index and how the data comes in, we have a number of fields within that data. In this case, let's say we have a host field for our Apache weblogs, and I want to know, for this particular host, what are the verbs that host sent to me? So how does Elasticsearch process that? So the first thing, Elasticsearch goes and looks in the host index. Now we're talking about actually indexing data, not the global structure. There's actually an index per field. Elasticsearch looks up the host that I requested. That points to a list of all of the documents that contain that value for the host field. So those are all of the documents, in this example, that contain that host sent. It then looks up the data on the verb field for all of those requests. And it constructs buckets based on what's in the data. It then computes a count, in the simplest case, to generate a histogram of the requests from that particular host. That is the basis for how Elasticsearch does all of the work that goes into the Cabana visualizations. Every Cabana visualization ends up as one of these kinds of queries. So within Elasticsearch, this is called an aggregation. An aggregation, again, is a collection of buckets and some metrics that I compute on those buckets. So in this case, I have a bucket for time that's going on the x-axis, and I have a metric of count. And what that gives me is I bucket all of my data into 30-second slices, and I count how many things are in that bucket. I get this graph, which is requests over time. But we can do much more complicated things This particular example is for the Apache weblogs of July 1995, and in this case, what we're seeing is the traffic that was requested for STS-70 and STS-71. For those of you who don't remember July of 1995, including me, STS-70 was a space shuttle, as was 71, and it turns out that STS-71 flew and landed on the 6th, and STS-70 launched on the 13th. And why did 70 launch after 71? Woodpeckers got into the fuel tanks, honestly. So, you know, this is, if I graph out my weblogs for that time period of July of 95, I can see the peak in interest for STS-71 happened in the beginning of the month and actually peaked on the 6th when it landed. And I can see the peak of interest that happened for STS-70 on the 13th when it launched. So I can build complicated things like this with different buckets and different ways of slicing my data and viewing it within Cabana. So that's what I got. Elasticsearch service allows you to run Elasticsearch in the AWS cloud. We take care of all of the undifferentiated heavy lifting, making it easy to deploy, scale, ingest, secure, monitor, and analyzing. So send us some log data today. Thank you.